Good afternoon. My name is Wimauki, and I'm an associate professor in the College of Computing and Informatics at Drexel University. Today, I would like to talk about large-scale data-intensive computing, and this will be a two-part video focused on this notion of data-intensive computing. This is also related to my research interest on information retrieval and large-scale web search. So dealing with large amount of data is part of our research projects. So it has been my focus and interest, and I'm glad to pick on this topic today. And let's start the journey together. So, um, so in the first part of the video, I would like to focus on the volumes and velocity of big data because it has a lot of implications on how we should build our infrastructure and be able to compute and generate and analyze data. So in the process of this overview, I would also like to cover some popular frameworks for data intensive parallel distributed computing. And then in the second part of the video, we'll focus on a hands-on exercise with the Spark machine learning library in Python. So, so again, the lecture today will be on large-scale processing and with machine learning and large-scale data analytics in mind. That is the purpose of this processing. And so we need to use distributed parallel computing, such as using the framework of MapReduce in order to be able to process, large amount of data given their volume and velocity. So Hadoop Spark are the popular, ecosystems or infrastructures, platforms, frameworks, whatever you want to call, for today's large-scale parallel distributed computing. And there is a Python interface to Spark for this purpose. So we'll focus on that in this part one of the videos. And then in the part two, as I said, we are going to do some exercises together, and the focus will be on Spark and some basic, operations when it comes to Spark. We'll do some setup together, very simple data set. Actually, we're going to deal with very tiny data just to demonstrate the ability to do it. Even though our purpose is for big data, it's an irony that we will work on a very small data set. But as long as we can demonstrate that capacity, as long as you have the infrastructure to support larger scale computing, the process is actually the same. So that will be the exercise with Spark machine learning and data processing. Now, and then finally, I would like to also have some questions for review and discussions at the end of this video. So big data, I think this should be an intuitive notion, because if you look at the amount of data that we have today on the internet or simply on the web, it's amazing how much we have, right? So today we have 4 billion internet users, 1 billion websites, 170 billion emails sent each day, 5 billion Google search queries, 5 million blog posts written each day, more than 500 million tweets each day, 5 billion video views on YouTube, 6+ billion gigabyte of internet traffic. So the list goes on and on. So there is truly a significant amount, and it's continued to grow exponentially. So this data is something That is valuable, of course, for potential analysis and predictions and use, but it also poses lots of challenges. And there are, first of all, different types of and sources of data, right? So if you look at the variety of data, they are in different types and structures. Some are highly structured, with specific consistent formats. When you think of a relational database or simply a set of spreadsheets, right? You have the rows and columns. They are very structured, and each column is most likely in a specific data type, such as numbers or strings. Perhaps there's a yes, no, no answer, from a survey question, things like that. So these are highly structured data. They are also semi-structured data, in the format of JSON or XML, right? They are quasi structured data, somewhat inconsistent, and then finally they are unstructured data, where there's no consistent format, right? So data such as articles written in human language, such as in English, or videos posted on YouTube, there's no particular format, no rows and columns that you can follow to identify each element in the data. It takes a lot more computing power and intelligence to be able to analyze that kind of data. So this is in terms of the data and variety. And just for these different types of data, we need different types of databases or data stores to be able to host all kinds of data, right? Traditionally, we have the relational SQL or SQL databases. Today, there are NoSQL or not only SQL databases, which can host, documents as, as data points. So so there are document stores where data are organized as a collection of documents. So things such as, MongoDB, CouchDB, or even Elasticsearch are such NoSQL databases. There are also key value stores, which simply store data as key value pairs, right? So, and this is also a kind of a very popular format for analytics, where you can quickly combine things together and aggregate for statistics. So, platforms such as Apache Cassandra, Dynamo, HBase, SimpleDB are examples of key value stores. There are also graph-based stores, data in which data are stored in the graph structures with nodes, edges, and properties. Neo4j, InfoGrid, Horton. So these are data where you can kind of abstract it as a graph structure. So things such as social network, or the interconnectivity of the internet, or the hyperlink structure of the web, right? You can think of it as, entities, and then lines or connections, arcs or edges connecting these entities together as a graph. So there are graph algorithms and that can be run and computed on these data types, and that require certain optimized stores for them. So these are just a few types of NoSQL databases or stores that are different from traditional relational SQL databases. Now, if we shift our focus to volumes and velocity, there is also a great challenge there, because it requires very intensive data computing. Given the amount of data that we have to deal with, and also the velocity of the data, the speed at which they arrive, right? Especially given lots of real-time streaming data, right? We have to be able to process them quickly enough, right, to be able to provide insight sometimes in real time. So a single machine hardware or software um, may not be enough. Sometimes, you have to be able to engage and employ more computing power, right? More than one CPU, right? You may have to use multiple cores or even graphical processing unit or GPUs to be able to run things in parallel in order to catch up with the speed. You may also have to, use a large number of computers, more than one computer, and distribute the task on many machines. And so in that case, you need you need parallel computing frameworks. And traditionally, we have MPI, we have grid computing, we have peer-to-peer computing. Lately, we have MapReduce, we have Hadoop Spark ecosystems, and we're going to get into some of these later. Right? So for the volume and velocity of big data today, right? Volume is about how big or the magnitude of the data that we deal with. Velocity is about the speed that we have to at that speed we have to be able to catch up with the data that is constantly arriving, right? So we know one machine is just normally is not powerful enough to process big data, and we need more machines, we need more CPUs, we need more GPUs, right? But with more, we also need to find a way to be able to divide data and computing for the many machines, for the many computing cores. And so questions are very important, including how you can divide the data, how you can divide the task to actually do the computation, right, for the analytics, and how you can coordinate and communicate the results, even the intermediary result, right? How do you put them together and say, I'm in progress on this part, whereas the other, nodes and computing power can be used for, other independent tasks in the same time, right? And then when the tasks are completed, how can you put them together and continue from there until you reach the final outcome? And then there is also a very important question of when you involve so many computers together, what if some machines fail, right? So if they fail, can we pick up from where they fail, and how can we coordinate all the machines together in such situations? So is there a principal way to manage all these within one framework? That is a very important question in today's big data environment. And the point here is that we need to have an infrastructure that can support all this, that can help us deal with large amount of data with the volume and velocity of big data today, and to support large-scale data-intensive computing. So having an infrastructure is key, because nobody can take care of everything that we discussed earlier, right? The failures, the coordination, the communication. So if there's an infrastructure, it can help us deal with all these issues where we can focus on kind of high-level analytics and the outcome of the computing, then it can save us lots of time, right? So having the infrastructure is key for the success of big data analytics. So here comes the framework of MapReduce. MapReduce is really a very important innovation, I should say, that makes things easier with a unified framework. And there are many different implementations of MapReduce, but here are some of the key things about MapReduce. It has this abstraction with two primary steps. So in MapReduce, there's a mapping process which applies to a piece of data and provides some intermediate output. And then there is this reducing or reducer process that consolidates the intermediate output and complete the final output. So things can be implemented in the mapper and reducer mechanism without worrying about the underlying mechanism for task distribution, coordination, and for tolerance. Because the framework, such as Hadoop, will take care of all that. And so you can focus on the high-level analytics task. And so developer can focus on high-level task and the algorithm development and implementation and testing, right? Without the low-level details. And so this is an overview of the big picture of MapReduce, okay? And so this is, the context of picture is of this kind of big picture is to show you, how does it work with MapReduce when it comes to aggregating and perhaps computing basic statistics about words. So let's say, you want to analyze text data, right? Articles and, pages or blogs. And so data that is written in human language. And one important statistic, one type of statistics is about the frequency of words. So, or how many times each word appears. So we need to count for each word how many times it appears, right? This is the frequency of the word. So this is a very fundamental task of many different text mining data analytics processes. And so how can we do that in MapReduce? So in MapReduce, given the input of text data with words and sentences and paragraphs, you can split, of course, tokenize the text into individual words. And then through this mapping mechanism, it's going to emit each individual word as some kind of a task to be aggregated. So you can emit the individual words and kind of distribute the piece of data to each worker, which in turn is going to reduce the data, or I should say aggregate the data once it encounters the same word for multiple times and count them. So mapping is, in a sense, to emit the data so that the reducers can aggregate them. And then and in the process of mapping and reducer, there are also other processes such as shuffling and combining to optimize the entire process. And then in the end, all the data can be merged and aggregated together. So the mapping, the reducing, all these processes can be distributed. They can happen on one machine, but they can also, more importantly, be conducted and computed on many computing nodes. And so this makes possible parallel distributed computing, given larger amount of data that has to be done, more efficiently. Okay, so with MapReduce, there are also challenges. The framework makes it kind of straightforward and make the developers of these algorithms focus on the algorithm itself without worrying about the low-level implementation or coordination. However, there are challenges associated with implementing related big data algorithms in MapReduce. Things such as, how do you convert an algorithm into this mapper and reducer abstraction? Sometimes this is not that straightforward. Sometimes the MapReduce process can be slow due to the data distribution and constraints in the algorithm itself. Sometimes iterative algorithms, which is quite often the case for network algorithms, for network analysis, can be very slow if you have to rely on the disk access. So part of the reason Hadoop was not that efficient is because when you implement iterative algorithms, and it heavily relies on disk IOs, which is slow, and it can slow down the whole process. So there are still lots of challenges in the MapReduce framework, but these over time are to some degree being resolved with newer implementations and ways of doing things in that framework. So now, in the early days of MapReduce, Hadoop was the major open source implementation of it, and now Spark is also part of the Hadoop ecosystem that may run on top of the existing Hadoop implementation of the cluster management, and it also interfaces with the Hadoop distributed file system, or HDFS, among others. So there is certain integration of Spark with existing Hadoop implementation. There are others in the ecosystem, such as Peak, to provide a high-level data flow programming language, Hive to provide SQL-like access, so you can run, SQL statements or SQL-like statements on top of Hive to be able to gather and aggregate data. There's also HBase, HBase that provides real-time data access. So there are lots of things going on with Hadoop ecosystem as part of Spark more recently. Now I have to say that Hadoop ecosystem was popular and tested widely. Lots of companies and research were done, did experiments with the Hadoop framework especially in the early 2010, but after around 2015, its adoption declined because of some of the major issues with such as over reliance of disk access, too much read-write to the disk, leading to very extremely slow performance on certain algorithms. So, but Spark, which is the kind of more recent development of the MapReduce, came in to fill the gap of this slow performance. It became much faster, especially with the use of memory instead of disk, because we know memory is much more efficient. Memory access can be 1,000 times faster than the disk I/O. So I think by utilizing memory, this Spark actually boosts the performance of MapReduce very significantly, and of course it's more expensive for large volume data intensive jobs because memory is more expensive to host data. So there is a trade-off between the cost and efficiency, but Spark has this major advantage of speed, right? So especially this is especially good for certain iterative methods, graph processing, real-time processing with very high volumes and velocity. And it also comes with this open source implementation of machine learning library that continue to expand in its capacity. So that is about Spark as a MapReduce implementation, more recent development. And so regarding Spark, it has this scalable machine learning library in MLlib that supports Java, Scala, Python, and R, different languages. And these are some of the most popular languages for data science and analytics. It can use existing Hadoop data sources on the Hadoop distributed file system, HBase, and so forth, and run crunch data from those sources. And it also implements many machine learning methods for clustering, classification, association, transformation, and statistical methods. So just to name a few. So there are lots of implementations available in Spark MLlib, and so feel free to try them out. Now, Spark also, in addition to MLlib, so at the bottom of the infrastructure is a Spark core that supports the basic functionalities, including the RDD or resilient distributed data set. And then on top, it provides the machine learning functionality in MLlib. And there is a Spark SQL, which is for SQL-like statements to be able to query the data on the Spark infrastructure. Okay, so for those people with experience of SQL or SQL, this is a great tool to use. And then there is also the streaming part that helps you deal with real-time data. Okay, so there's a lot of capacity in Spark. And so in the second part of the video, we're going to talk about discuss work on a hands-on exercise with Python, and we're going to connect to Spark using PySpark. And so with PySpark, you can connect to Spark from Python. And if you are familiar with the notebook environment, Jupyter Notebook or Google Colab, you know what I'm talking about. You can use Python code to connect to Spark and take advantage of that capacity in Spark. And if, of course, if you have the infrastructure set up in Spark that employs lots of machines, you can take advantage of the cluster of machines as well. So you have, you potentially can have lots of computing power depending on your setup and configurations. And so with that connection to Spark, you can utilize functions in Spark to mutate, to select, to filter, to summarize, to arrange data. You can manipulate data on Spark. You can collect them back to the notebook to report back to the stakeholders if you want. You can use Spark's distributed machine learning algorithms to perform certain analytics. You can also extend existing functions on Spark by implementing your own methods and kind of plug into the Spark ecosystem. So these are some of the things that you may be able to do with Spark. So that is the end of this overview of big data, some of the challenges that we encounter today when it comes to large-scale data-intensive processing, especially given the volume and velocity of big data, and then existing frameworks that we may want to take advantage for this purpose, to be able to help us crunch large amount of data at a very high speed. And so with that, I would like to conclude this presentation with just some of the questions that you may want to think about, right? So I think this notion of big data can be intuitive. There are multiple V's, volume, variety, velocity, and so forth, that are normally attached to the notion of big data. But what is your definition of big data? What do you mean by big in the big data? Perhaps people have different challenges associated with big data. You can also think about what is the largest data set that you have ever processed, What did you do with that? What were the result? Sometimes perhaps it's not the largest data set that you have used, but perhaps the computing is the most intensive, right? You can also think of that way from the point of view of computing that is necessary to deal with that amount of data. And then what do you think is the next major breakthrough that you think will happen in computing informatics, right? Things that can be related to big data. Do you think we will be able to have the necessary capacity to be able to process the amount of data that we generate today? This is one related question. Perhaps there will be a major breakthrough in this, either associated with quantum computing or other, areas of computing. What is the difference between parallel computing or processing and distributed processing? And given examples of decision making where you can trust an algorithm to make as good or better decisions as a person. So think about some examples. Perhaps, you can run analytics on large amount of data, but in the end, if it makes a prediction or if it gives any advice or suggestions in terms of what you should do based on the outcome, do you tend to trust that analysis or the outcome of the analytics? Right? For what task would you trust human judgment more than an algorithm? Why? And certainly, I know certain algorithms can be a black box. Can you trust a black box simply because it has crunched a lot of data? Right? So additional things you may do, again, in the second part of the video, we're going to set up a Hadoop, Spark environment in Colab, and then do a very small task with that. Okay, just to have a sense of how it works. But perhaps for those of you who are technical enough and confident to set up a Hadoop or Spark cluster on multiple machines, run a basic task, such as a task is, word counting. Do you think it runs faster than a simple job on one machine? Can you tell that multiple machines together can actually beat the single machine, right? If not, what is the purpose of setting up a cluster, a distributed cluster on multiple machines, right? And then find perhaps a big enough data source that you have access to, and they can justify processing with more than one single machine and do something interesting with that. So I think these are things that you may do, and I think it will be interesting and happy to know what comes out of that. So with that, I would like to conclude this video with the overview. It runs actually longer than I expected. But anyway, so I hope this is helpful, and keep me posted if you have questions, and I will see you in the next video on the hands-on with Spark and a small data set that we want to crunch. So see you in that video. Bye bye.